Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a quartic complex equation. Probably one of the easiest quartics you can ever get, probably, right? If you replace the 4 with 1, it would still be the same level of difficulty, I think. And by the way, I rank my problems easy, medium, and hard. Let me know if you don't agree with the ranking and if you think a problem would be in a different category. Anyways, I also have another channel called Cyber Math. You probably came from that channel, maybe, because I also talk about aplusbi on that channel. Kind of what is it called? Multi-level marketing, cross-level marketing. Anyways, cyber with an S. Okay, so how do we solve a problem like this? By the way, if you're new to complex numbers, go ahead and check out my lecture videos and ask questions. That's the best way to learn. Try hard and ask questions. And don't give up. Ever. Never, ever. Okay, so how do we solve a problem like this? I'll be presenting two methods. Okay, ready? First method. So for my first method, I'm going to go ahead and solve this problem by factoring. Why? Because it's factorable. Wait a minute. This looks like sum of a fourth power and a perfect square. You can think of it as sum of fourth powers, obviously, because there's something called a to the fourth plus 4b to the fourth. Remember that? It's called Sophie-Germain. How does Sophie-Germain work? Sophie-Germain formula works by completing the square. Not the quartic, completing the square. Maybe there's another way to approach it, but this is all I know. So here's what we're going to do. First of all, notice that this is z to the fourth is z squared. So if you add to this 4z squared and subtract it, you're going to get a perfect square with the first three terms and another perfect square being subtracted. In other words, you get difference of two squares. Isn't that amazing? It's beautiful. Now we're going to write the first one as z squared plus 2 quantity squared, because that's what it is, and the second one as 2z quantity squared. So now we can clearly see, hopefully, that we have a difference of two squares. And how do you factor a squared minus b squared? You write a plus b times a minus b. And a and b don't have to be real, by the way. I think this also works with complex numbers, especially in the complex world when we do the absolute value squared. Remember, we could factor it into a plus bi and a minus bi. Did you know that? We could factor sum of two squares. But this is a little different. Okay? So let's go ahead and use the formula for difference of two squares. This will give us z squared plus 2z, or not 2z. That's the problem. Okay, do you see what I see? And then z squared plus 2 minus 2z. And I make my z's with a little line so that they don't look like 2's, because my 2's look like z's. You know, anyways, my 7 is like this, not like this, but it's more like this. Actually, oh, okay, I'm sorry about that. My 7's are like this, not like this. That's the American 7. This is the European 7. Why? Because this 7 looks like 1, or upside down L. Anyways, that's another story. Let's go ahead and what are we going to do? Oh, yes, set it equal to 0. But write this in standard form because it looks better. And, you know, math people are very obsessed with standard form, polynomials. Now, these are two quadratics. Isn't that amazing? Like, we were able to factor like crazy. Yes, because thanks to Sophie-Germain, thanks for coming up with this formula. I think Sophie-Germain, by the way, is a German mathematician. And we don't have a lot of female mathematicians in history, do we? Anyways, so how do we solve this? Each of these equations with the quadratic formula, negative b plus minus the square root of b squared, 4 minus 8. Uh-oh, that's like negative 4, so that's going to be like 2i, right? Uh-oh, I got stuck at the highlighter, divided by 2a. And from here, we're going to get negative 1 plus minus i. Nice. And the other equation gives us more solutions. Z equals negative b. This time we get a positive, but the sign in between doesn't change. So that this gives us 1 plus minus i. Uh-oh, we got like 4 solutions. Beautiful. And it's a quartic, so that's normal, right? Now, take a look at this. These two numbers should be somewhat familiar to you. Do you remember them from other problems that we made? For example, if you take 1 plus I and square it, what do you get? 2i. Hopefully you remember that, right? or you memorized it, in other words. What happens if I square both sides one more time? You get 4i squared, which is negative 4. Uh-oh, that's what I was trying to get. So if you take 1 plus I to the 4th power, you get negative 4. So z is a solution. Make sense? That's the whole idea. Of course, 1 minus I also works because it squares 2i. I mean negative 2i, but its square is going to be negative 4 again. And what about the other ones? Those are negations, so they'll work as well. You see the whole idea? So we could use this idea maybe like as a third method, like, okay, I know that 1 plus I to the 4th power is negative 4, so that's a solution. How do you find the other solutions? Given that this is a polynomial with real coefficients, right? Z to the 4th plus 4 equals 0, has no complex or non-real coefficients. Therefore, the roots have to come in conjugates. But how do you find the other one? Maybe you could do this. You could write it as follows. Square root both sides. You're going to get something like the square root of negative 4, which is plus minus 2i. And then hopefully you could go from there. Make sense? Okay, I hope it does. This is another idea that you could probably insert as the third method. But I still need to show you the second method because I showed you the first and the third. Now is time for the second method. Are you ready? Okay. The second method actually uses more complex ideas because it's going to use Euler's form or exponential form, or should I say polar form. Euler is amazing. I always say that because I think he's just amazing, unbelievably amazing. So we're going to go ahead and use the polar form. But how to use that? Let's go ahead and subtract 4 from both sides first so we can kind of bring it into an equation where one complex equals another. Now we need to turn the right-hand side into the polar form. If you remember, the argand plane, we have negative 4 here, and its distance from 0 is 4 units, and it makes a degree, angle of pi radians with the real axis. This is real, this is imaginary, this is called the argand plane. The D is not silent, don't get me wrong, okay? That's probably the name of a person, I don't know. So, here's what we can do. The modulus is 4, here, the distance. So, any complex number can be written as r e to the I theta. So, negative 4 can be written as 4 times e to the power I pi. But pi is not the only angle, because if you add 2 pi to it, it brings you to 3 pi, which is the same as pi, sort of, right? It looks different, but so we're going to do the following. We're going to add 2 pi n or multiples of pi to this. Some people express this as follows. They say, oh, okay, we're going to have odd multiples of pi and then I. Cool, you can write it that way too, that's fine. Now we're going to go ahead and divide both sides by 4. I mean the exponents. Raise both sides to the power 1/4, and guess what? You're going to get the 4th roots of this number. And you can do that by multiplying this number times I, or just divide the pi by 4. Make sense? And 4 to the power 1/4 is square root of 2 because it's the real value. This is real, by the way. And it can't be negative. And it's the 4th root of 4, which is square root of 2. Great. What about this one? So there's multiple solutions, obviously, right? For example, if n is 0, you're going to get z equals root 2 times e to the power I pi over 4. What is I pi over 4? It's cosine pi over 4 plus I sine pi over 4. Thanks to Euler, he came up with this formula, and it's just mind-blowing. Don't you think so? So if you go ahead and multiply by that, you're going to get one of the z values. The rest is yours, okay? Because I'm only going to do one because I'm lazy. Now, cosine pi over 4 is root 2 over 2, and sine pi over 4 is same. So now this gives you what? Z equals 1 plus I. It's one of the solutions, but the others are going to be very, very similar. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.